In the early 2000s, General Electric gambled everything on a radical idea. Create a jet engine so advanced it could slash fuel burn, rewrite emissions standards, and transform global air travel, the GEnx. But behind its reputation for reliability and efficiency lies a series of high-stakes risks, technical gambles, and near-miss disasters most airlines never talk about. So what was the real price of chasing aviation's future? And how did an engine built for the Dreamliner nearly become GE's nightmare? When Boeing set out to design the 787 Dreamliner and revamp the 747-8, it demanded a leap in propulsion technology, something lighter, cleaner, and more efficient than anything in the sky. General Electric answered that call in 2004 with the GEnx, starting from a blank sheet. The goal was clear: deliver an engine that could satisfy the twin giants of long-haul aviation, meeting unprecedented targets for fuel burn, emissions, and reliability. Airlines wanted lower operating costs and a smaller environmental footprint, and Boeing's new airframes would accept nothing less. GE's engineers made a bold move by centering the GEnx around composite materials. For the first time in commercial aviation, both the fan blades and the fan case would be built from carbon fiber composites. This innovation wasn't just about shaving off a few pounds. Composites resist corrosion, tolerate extreme stress, and allow for more aggressive aerodynamic shapes, essential for squeezing out every bit of efficiency. The result? The GEnx would weigh hundreds of pounds less than its predecessors, a critical advantage for airlines chasing every drop of fuel savings. The program's foundation rested on the idea that advanced materials and cleaner combustion could deliver real-world sustainability, not just marketing slogans. GE's design team, drawing on lessons from the GE90, aimed to push the boundaries while keeping reliability at the heart of the project. Their work set the stage for a new era of jet engines, where the structure itself became a tool for environmental progress. Dale Carlson's team knew the promise of composites was only the beginning. Achieving Boeing's targets would take riskier leaps, especially in the engine's hottest, most punishing zones. For the GEnx combustor, GE introduced the Twin Annular Pre-Swirl, or TAPS, system. Unlike traditional combustors, TAPS premixes fuel and air, producing a cooler, leaner burn. The payoff? Nitrogen oxide emissions dropped by 55%, meeting environmental standards few thought possible in a wide-body engine. But this leaner flame demanded materials that could survive relentless heat and pressure. In the turbine, engineers turned to titanium aluminide, or TiAl, a brittle, lightweight alloy that shrugs off temperatures that would soften ordinary titanium. Each TL blade saves precious pounds, but manufacturing them at scale pushed the limits of metallurgy and quality control. Even more radical, ceramic matrix composites found their way into the hottest sections, offering heat resistance beyond any metal, yet raising questions about long-term durability under real airline schedules. The composite fan case alone shed over 300 pounds compared to metal predecessors, but every new material brought unknowns. Carlson's gamble was clear. Only by stacking these innovations, composites for weight, TiAl for heat, TAPS for emissions, could GE hope to deliver on its promises. The GEnx would become a proving ground for the industry's boldest materials, setting the stage for the stress and scrutiny that would follow. During a critical test in 2006 at GE's Peebles facility, engineers fired up a GEnx prototype and deliberately forced a fan blade to break loose at full speed. The blade tore away from the rotor, slamming into the engine's containment ring with the kind of energy only seen in worst-case scenarios. The ring held, as designed, but post-test analysis revealed weaknesses at the blade root and in the containment system. Engineers pored over the data, finding that while the engine met minimum safety standards, the margins were uncomfortably slim for a product about to enter global service. Reinforcements were quickly ordered for both the blade attachment and the containment casing, adding months to the test schedule. While the technical team scrambled to address these findings, another battle was brewing behind the scenes. The new titanium aluminide turbine blades, crucial for weight savings, depended on a single supplier struggling to deliver consistent quality. Internal memos from 2008 reveal heated exchanges between GE's procurement division and the materials team. Procurement pushed hard to keep costs down, while engineers warned of premature wear in early test blades. The dispute delayed initial GEnx-2B deliveries for the 747-8, forcing GE to renegotiate supply contracts and impose stricter quality controls. These early setbacks sent a clear message. Pushing the limits of new materials meant the old ways of testing and supplier management were no longer enough. With the clock ticking and Boeing's production lines waiting, every delay carried the risk of missing market windows and eroding confidence among airline customers. The pressure to deliver a breakthrough engine was now matched by the pressure to prove it could survive both the lab and the real world. On July 28, 2012, a Boeing 787 powered by a GEnx-1B engine sat on the tarmac in Charleston, South Carolina. During routine taxi testing, the engine's fan midshaft fractured without warning. Metallurgists traced the failure to environmentally assisted cracking at the thread root, triggered by a switch to lead-free dry film lubricant and graphite grease, an attempt to comply with new chemical regulations. The NTSB, under docket DCA 12IA114, issued an urgent call for ultrasonic inspections across the global GEnx fleet. Within weeks, a second cracked shaft surfaced in another undelivered 787. Airlines grounded aircraft as GE engineers, led by Chuck Nugent, raced to halt the problem. Nugent's team reversed the lubricant change, reinstated legacy assembly chemistries, and rewrote inspection protocols. The FAA followed with an airworthiness directive, mandating regular shaft checks and barring flight until every engine passed. No sooner had the midshaft crisis been contained than a new hazard surfaced at altitude. In early 2013, GEnx-powered jets began losing power in clear air above the tropics. Investigators found that high concentrations of tiny ice crystals, undetectable by standard systems, were bypassing anti-ice defenses and collecting deep in the engine core. When the ice suddenly broke loose, it triggered compressor surges and thrust rollbacks. The phenomenon, known as ice crystal icing, forced a rapid industry response. GE's fix relied on a major update to the FFA-DEC software, introducing a new control law for variable bleed valves. This allowed the engine to clear ice before it could cause damage, based on meteorological cues rather than temperature alone. The software overhaul, completed in just 12 months, restored operational reliability. Airlines also received new flight manual procedures, instructing crews to avoid convective weather and monitor engine performance in high-risk areas. Each fix carried its own lessons. For Chuck Nugent and his teams, the experience reinforced that innovation in materials and software demands relentless vigilance. Awesome. Not just in the lab, but in every corner of the globe where engines fly. Regulatory action, transparent investigation, and rapid technical response became the new standard for restoring trust and keeping the GEnx at the heart of modern aviation. Across the world's busiest long-haul routes, the GEnx engine has rewritten the numbers that matter most to airlines. Fuel burn drops by up to 15% compared to the engines it replaced, translating directly into lower costs and smaller carbon footprints. More than 3,000 GEnx engines have been ordered, and the fleet has now logged over 50 million flight hours, powering aircraft for more than 70 airlines on every continent. Airlines measure reliability in time on wing and dispatch rates, and the GEnx consistently leads its class, with extended ETOPS certification, allowing twin-engine aircraft to fly routes up to 330 minutes from the nearest airport. An operational flexibility once reserved for only the most trusted designs. Noise levels are down by as much as 30%, thanks to slower-turning composite fans and advanced nacelle shaping. These aren't just engineering milestones. They're the hard proof that advanced materials and design choices have delivered real, measurable benefits in the skies. In 2018, the GEnx engine became the first commercial jet engine to incorporate an FAA-approved 3D printed part, a simple bracket known as the PDOS. This milestone was more than a manufacturing upgrade. It signaled a new era in how jet engines are designed, built, and maintained. Additive manufacturing allows engineers to create complex shapes with less material, reducing both weight and waste. For GE, these lessons from the GEnx program have become the foundation for even more ambitious projects. The company's RISE initiative, short for Revolutionary Innovation for Sustainable Engines, draws directly on the composite structures and lean burn combustion pioneered in the GEnx. The goal is clear: achieve a further 20% reduction in fuel burn using open fan architectures and hybrid electric compatibility. GE Aerospace calls this a leap forward in efficiency and sustainability. With each advancement, the boundaries of what's possible in propulsion are redrawn, not just for today's aircraft, but for the next generation of flight. The GEnx stands as a bridge, carrying hard-earned knowledge from years of innovation into the future of aviation. Since entering service, more than 3,000 GEnx engines have powered aircraft across 70 airlines, logging over 50 million flight hours. The documentary has shown how General Electric's bold use of composite materials and advanced combustion technology cut fuel burn by 15% and reduced emissions and noise. Yet, the GEnx story is also marked by early setbacks, such as the 2012 fan midshaft failure and the 2013 ice crystal icing issue, documented in NTSB reports and regulatory filings. While GE publicly addressed these failures with engineering fixes and software upgrades, the full details of supplier disputes and certain design decisions remain undisclosed in available records. Today, the GEnx stands as a proven platform for efficiency and reliability, and its innovations are shaping GE's next generation of engines. The evidence confirms that the GEnx was not just a leap in technology. It set new standards for sustainable aviation, with its legacy unfolding in every flight hour recorded.